Okay, so we finally get to calculus today. Yay! All right. So this is still might be review for some of you, depending on who your calculus teacher was, and also like when, because I know I got to this with some of my pre-cal students, but not all my pre-cal students. So this may be brand new. This may be familiar. Okay, but now we're finally going to get into calculus. Okay, so we are studying kind of two major branches of calculus. The first is differential calculus. That's what we're going to be jumping into today, and then later we'll be studying integral calculus. Both of them have to do with kind of calculating things in very small intervals, okay, of time and stuff like that. In fact, at instants of time, right? So here, or adding up an infinite number of things too later on in integral calculus and getting like a finite sum. But for right now, we're going to focus on what was essentially a single problem that led into then calculus, okay? And that is called the tangent line problem, okay? So the goal of calculus was kind of developed in order to solve the idea of trying to find the slope of a curve at a single point, right? So I'll just go through this here just to make sure I don't miss any points. But essentially, the problem of finding the tangent line at a single point P boils down to the problem of finding the slope of the tangent line at point P. Okay? So finding the equation of a tangent line, we really just need to find the slope, because once you have the slope of the tangent line, you have a point at that tangent point, and you can then write the equation of a line. Okay? By the way, when I mean tangent line, right, okay, it's kind of like a similar idea if you remember tangent lines from geometry, right? A tangent line in geometry was a line that would intersect a circle at exactly one point, right? And not go through the circle, but stay on the outside. Likewise, a tangent line in these situations, right? We're trying to find the equation or the slope of a tangent line that intersects our graph at only one point, okay? It's kind of touch, well, in the local neighborhood there, I guess I'll say, okay? So anyway, one way to kind of like get a good approximation of the tangent slope is to use the slope of a secant line. Secant lines use 2 points. So for example, here we have a nice curve of function f, okay? And we've got some points on that curve, all right? And we're going to find the slope between those 2 points. You may remember doing this back in like Algebra 1, for example. Okay, you did this a lot. In Algebra 1, or Algebra 2, I mean. Sorry, not Algebra 1, Algebra 2. Okay. But anyway, so let's focus on that. Now we're going to set this up in a slightly unique way, though. We're not going to just come up with some random variable here that then matches to these 2 points. We're instead going to think of this as we have a point C, it's matching point f of C, right here, it's matching y coordinate there, f of C. We're going to go out, bless you, some length here, and we're going to call that length delta x, a change in x, right? So we're going to go out some measurement of x from that C value, which then would result, what would be an expression for this x coordinate right here? If we started here at C, we're going out delta x from that C, what could we describe this as? C plus delta x, right? Starting at C, adding delta x to it, C plus delta x, okay? And then if that's the x coordinate, applying the function to it, how can we describe the y value of that point? F of C plus delta x. Exactly right. Okay? F of C plus delta x. And so, you're like, wait a minute, this is starting to sound like something that we've seen before. And it is, right? So let's imagine then find the slope between these 2 points. I'm going to try and draw our secant line here. Okay, so the slope of the secant, I'm going to say m sub secant, so it's like the slope of the secant, right? M sub secant is equal to, remember it's like it's y2 minus y1 over x2 minus x1, right? It's the slope formula. Okay, but of course for us, we have, some names for our y coordinates here. We'll say f of C plus delta x minus f of C all over C plus delta x minus the delta x. Sorry, minus C. There you go. The other x coordinate was C there. Okay. So f of C plus delta x minus f of x all over c plus delta x minus c there, those 2 points. Okay? I don't want to crowd the space there. All right, but of course this simplifies just a little bit, right? The numerator will keep the same. That really can't be simplified right now. But the denominator, we have a c and a minus c, and that's going to cancel then and leave with just delta x. Okay. And so then this is the slope of our secant line, okay, for this particular situation, this scenario, the way we set it up. Okay. There's your y2 minus your y1, and of course the x is kind of simplified a little bit, so we're left with just the delta x. Okay. The slope, okay, conceptually, you also may remember it from Algebra 2 as the average rate of change. Okay? The average rate of change. Average rate of change. Okay? It's not at an instant, it's the average between 2 points. Average rate of change. Okay? And again, I know that's something that you did in Algebra 2. It's a common question that was asked, I feel like, finding the average rate of change. So that's average rate of change. But of course, what if we wanted to find the slope of a line at a single point instead of 2, right? What if we wanted to do that tangent line now? How can we use this? What can we do? Well, so let's try and imagine that here. Here again we have a curve, okay, f. All right, so there's our function f there. We have our y-axis and x-axis right here. So let's try and find the slope of a line at this single point. But of course the problem is here that when we go to do our slope, the y values, okay, f of 1, well, here's 1. So f of 1 is going to give us 2. And then f of 1 again is going to give us 2. And then 1 minus 1 because of the x-coordinates there. And we end up with 0 over 0, right? And so that's like indeterminate. So our kind of slope formula fails us a little bit here. All right? Trying to find the slope at a single point, we run into some issues. We use the slope formula and we get 0 over 0 indeterminate form. Okay? But let's try another idea here. So instead, we'll find the slope for this secant line right here. Okay, so let's find the slope of this secant line. Okay, that slope. All right, so it's going to be, f of 1, f of 1, that point right there, and then also negative 1, f of negative 1 there. So we'll use these 2 points. That's represented right here. Okay, and so f of 1 is 2 minus f of negative 1 is also 2 over, but now it's 1 minus a negative 1, so it'll be 1 minus negative 1, which is plus positive 1. So you get 0 over 2, or the slope is just 0. Okay. So again, while we had trouble finding the slope at a single point, using those 2 points, no problem. And again, it's not a big surprise there. It's a horizontal line, so of course we should have gotten a slope of 0 for that secant line. But now, let's take this point. We'll keep this point still because, again, we really wanted to try and find the slope at this particular point right here, right? We got indeterminate. We started with a secant line. Let's move this point in a little bit closer here to this point right here. And do the slope of this secant line. Okay. So that's secant line. Okay, yeah, you can count the slope there. It'll be negative 1 will be the slope, right? We're going to go down 1, right 1, down 1, right 1 there from those points to those points. Okay, again, I'll just do the math here real quick though too. So it'll be 2 minus 3 over 1 minus 0. So negative 1 over 1, okay, is our slope there. Okay, and you'll also notice here, right, that maybe, looking at this point, trying to determine the slope at this particular point, okay, it's kind of hard to see, like, well, what that might be, but, you might want to think, well, again, if my pen were like the tangent line, like maybe that tangent line would look something like that, right? Visually, we can kind of like, see, like if I only want to touch this point, okay, and not really go through the graph, like maybe our tangent slope would look something like that. As I take my slope here, right, slope of 0, I move this point in closer. Now my secant slope is a closer approximation, right? I mean, it's like now at least it's negative. Before it was a slope of 0, but now as I move that point in closer to the point whose slope I want to find, It's making that a little bit better of an approximation, right? It was 0. Now at least it's negative. And if I bring that point in even closer, it's going to get closer and closer and closer until eventually it's going to be the slope of that tangent slope there. Okay, question, please.
Why is it called the secant line?
Secant, because that's the name for a line that intersects the curve at 2 points, right? If you remember that back in geometry, when you were talking about circles and lines and stuff like that, a secant line was a line that intersected your circle at 2 points. That's all, yeah. I'm sure there is some sort of relation to it, like in trigonometry and stuff like that for secant there, but I don't know what that is right now. So, yeah, Cindy?
What would be the answer to that question?
So the answer is we don't have an answer just yet, but we will in just a little bit here, right? So right now, but you can see, do you see the purpose of this more as the principle that using the secant line, if we bring our other point closer and closer and closer to the one whose slope we want to find at this particular point, if we bring the other point in closer and closer, we get a better approximation the closer we get. That's the principle there. Okay, so back to this. So now we're going to try and find a method that tells us the slope at any single point. Now we're going to use that, a single point using the slope formula. Okay, and for our purposes, we're going to do it at x at c. So I'll say at x equals c. Okay, we're going to choose this particular point. Okay, so we want to find the slope at this point right here. Alrighty. So again, same setup. We're going to start with c. We're going to go back to that setup that we used for the secant line. So we'll go out delta x. That leaves this to be c plus delta x, and this to be f of c plus delta x. Okay. And again, we're going to go use our secant slope. So if you remember, again, the slope of the secant line was f of c plus delta x minus f of c all over delta x. I'm going to leave it in the simplified form that we came up with. Okay, so again, just redoing what we did before, except now we are specifically trying to figure out a single point. Okay? Find the slope at a single point. So, with the way I've set this situation up here with the graph, I got 2 points, but I got those 2 points by taking my original single point, c, adding a delta x to it to get my other point. Okay? If then I wanted to find the slope at a single point, I could say this delta x, I could set that delta x to be 0. If I said delta x was 0, equal to 0, this point would be 0 units away from this point, so it'd be the exact same point, right? And so if I try though, so for a single point, delta x equals 0, okay? But if we put in 0, we get f of c plus 0 minus f of c over 0. Right? So we plug in 0 here to try and find that slope at a single point. And we get f of c minus f of c over 0, which is then 0 over 0, and it's an indeterminate form. Okay. Indeterminate, meaning there could be a value here, right? We've seen in the past where we could have values, okay? We could be approaching a value here. We just don't know, right? Or it might be, just that's what it is. Okay? So we can't equal 0. To get the slope at a single point. We can't equal 0, but we can approach it. And what thing in math allows us to approach a limit? Exactly right. Okay, so we use limits. All right. And so that's where we then get the slope of a tangent line. Okay? So I'm going to jump down here to this section and actually write the definition for the slope of a tangent line. It is the limit as delta x approaches 0 of f of, and I'm going to use x plus delta x minus f of x all over delta x. Okay. And so there is you can think of that as like the m sub, tangent, or the slope of a tangent line. That is it. Okay, that is the slope of our tangent line. All right. This is an important definition to know. Okay, just like the intermediate value theorem, this is something we want to be familiar with, right? We'll be working with it a lot, so you'll gain some more familiarity with it too. So if f is defined on an open interval containing c, and if the limit exists, then the line passing through the point c, f of c with slope m is the tangent line to the graph of f at the point c, f of c. Okay, so the slope that we get from this combined with the single point here, c, f of c, okay, you write the equation of a line using the slope that we get from this and this point right here, and then you come up with that tangent line that's tangent to the graph of f at that point, c, f of c. Okay? Okay. The slope of the tangent line to the graph of f at that point is also called the slope of the graph of f. So sometimes instead of referring to the slope at this single point as the tangent slope, you can also just call it the slope of f at that particular point. Okay, at x equals c. This is also known as the instantaneous rate of change, right? And it makes sense that we call that an instant because we're finding the rate of change of this thing at a single point, not using 2 points and like the average, right? But finding the instant slope at an instant. That's known as the instantaneous rate of change. Okay, so slope of your tangent line, slope of the function, instantaneous rate of change, synonymous concepts. All the derivative value at a particular point. Okay, slope of the tangent line, slope of the function, instantaneous rate of change at a point. Those are all saying the same thing. The value of the derivative at a particular point. Okay. So, wow, all that theory. Now let's put it into practice. Okay, so we want to find the slope of the graph of f of x equals 3x minus 1 at the point 2, 5. Okay, so go 1. Let's graph this thing first. Let's kind of get a good look at it. Okay, so -1, up 1, 2, 3, right 1, up 1, 2, 3, right 1. Okay, so there's our line. And we want to find the slope at the particular point 2, 5. Okay, right there. There's 2, 5. Okay. So since we're trying to find it at the point 2, that's going to be like our x value there. So I'm going to set up my tangent slope, the limit as delta x approaches 0, of f of x plus delta x minus f of x all over delta x. Okay. Since I want to find it at the specific point of 2, 5, you'll notice there's no y's in here. There's no y's in this slope formula, right? Okay, so we don't need to worry about the 5, but the 2, that's our x value. So we're going to plug that 2 in for the x's here, okay? Delta x's, remember, are a different variable. So we'll plug in, make it f of 2 plus delta x minus f of 2 all over delta x. Okay, and now we'll evaluate. Okay, so 2 plus delta x, we want to take f of that, so that 2 plus delta x, we'll replace the x here, so it'll become 3 times the quantity, 2 plus delta x, and then there's a minus 1. Okay, and then minus f of 2, well, we know what f of 2 is, it's 5, right? If I plug 2 in here, 2 times 3 is 6, minus 1 is 5. So, I mean, you can do it that way. Maybe I'll show the work. Okay, and again, just to highlight this, because this is tricky, right? This substitution here. So this came from this right there. Okay. And that came from that right there. Okay, yes, Clayton.
So you just put the slope for f. How did you get the 3 there?
So we're evaluating what is f evaluated at 2 plus delta x, right? And so if that's f of x is 3 times x minus 1, I'm taking that 2 plus delta x, which is replacing the x there, I'm going to replace the x here. So it's 3 times 2 plus delta x minus 1. You see what I'm saying? It's just plugging in that 2 plus delta x. And now we simplify. So let's see here. It'll be 6 plus 3 delta x minus 1 minus, and that's going to be, let's see, 6 minus 1 is 5, so minus 5. Okay. And then what cancels here? What can we get rid of, or what can we do in the numerator there? Yeah, so 6 minus 1, 5. Minus 5, 0. So the 6 minus 1 and 5 all cancel out together. And then we're left with the limit as delta x approaches 0 of 3 delta x over delta x. And now what can we do? Cancel out the delta x's, and we're left with, well, 3. There's no other delta x's left over for us to plug in 0, so we'll just say our answer is 3 there. Okay. Now, we could have, at any point prior to this step, evaluated the limit by plugging in 0 for delta x. But the problem is, if I had plugged in 0 for delta x at any of these previous steps, we would have ended up with 0 over 0. Now that we used our limit strategies here, and the delta x is eventually canceled out, we were able to evaluate this, and it's just 3. So, the slope of the graph of this function is 3 at the point 2, 5. Why does this answer make sense? What's that? The slope of what is 3? Yeah, of the line. Yeah, the slope of the line. It's a line, right? It's something that any Algebra 1 student could do without having to use calculus. No big deal, Mr. Widmeyer. But again, at least it shows that our derivative formula works here. Okay? But that's not very impressive, right? Because we already knew the slope of that was 3. So let's do another one here with this one. Okay? So, any questions up to this point? All right, so then example 2, find the slopes of the tangent lines to the graph of, x squared plus 1, right? We can't ask an Algebra 1 student what the slope of this would be. They wouldn't know, right? An Algebra 1 student would know what the slope of that is, but they wouldn't know what the slope of this is, right? And nor do we necessarily, right? But we can find it using the derivative. So, let's again sketch the graph of this real quick. So, 1, 2, 3, 4, 5. Okay, so let's see here, 0, 1, and then 1, 2, 5. So it's our parent function of a parabola, shifted up 1, so there's the graph. Okay, and again, we're going to evaluate the slope at 2 points. We're going to do it at negative 1, 2. And then also at 0, 1. Now again, I've done this before with my pre-cal class, so we're going to do it again here. But you guys already have an intuitive sense about what your tangent slope is going to be here, right? I mean, for example, you know, again, if you'll permit me to kind of use my pen as a model for a tangent line, right? If I were to take my pen and kind of try and place it so that I'm only going to just touch this point and not actually like go through the graph, but just touch it, be tangent to it. If I put my pen, my tangent slope would be something like that. So while we maybe can't determine what the slope value, the number precisely is going to be, we can at least say it's going to be positive, negative, or 0 here. Negative, right? We're going down as you go from left to right. So the tangent slope here would be roughly negative, right? All right. At the bottom, well, we'll hold off on that. What about, let's pick a point over here, like this point right here. If I make a tangent line right there, okay, what's the sign of that tangent slope going to be? Positive, right? We're going up, right? And then what do you think is going to be the tangent line slope right here? Yeah, right? We would think it's going to be 0 because right there at an instant, it's bottoming out. and then goes right back up. So let's check and see if that works. We'll check the -1, 2 first, okay? So let's find the slope of the tangent at x equals -1. Okay. Again, for these derivatives that we're doing, they all only have x's in them, right? And so for the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay. We don't need to worry about what the y coordinates are at those points. The y coordinates don't have any bearing, okay, in this formula here on on the slope. Okay. So we'll plug in -1 here. For our x's. Okay, plug in that -1. And then we'll simplify. Okay. Again, probably one of the hardest things to do is this substitution right here. Figuring out what is f of -1 plus delta x. But again, we go back up to our function. The -1 plus delta x is what we're substituting into our function. So it's going to be the quantity -1 plus delta x squared plus 1, okay, minus the quantity f of -1. All right, and if you'll permit me, I'll just go ahead. We know what f of -1 is. It's 2. So I'm just going to go ahead and skip that step this time. Okay. But again, I'll try and highlight things here. This f of -1 plus delta x, that is this piece right there. Okay. The -2 is the minus f of -1 right there. Okay. So just so you know what matches to what there, where we got those things. All over delta x. Okay. Now we need to simplify. In order to simplify this, in order to square it out, we're going to have to FOIL here, right? -1 plus delta x, we have to FOIL that out. So it becomes 1 minus 2 delta x plus delta x squared plus 1 minus 2 all over delta x. Does anything simplify in this scenario? Does anything simplify in this scenario? Yes. What can cancel out? Okay. 1 plus the 1 is going to make 2. Minus 2 will give us 0. So the 1 and the 1's and minus 2 will cancel, make 0. Okay. Well, great. I have a delta x in the denominator and a delta x in the numerator. So I can just cancel out this delta x with the delta x squared, and it'll be -2 delta x plus delta x. No. How can we can simplify here, but what do we need to do in the numerator? Factor out a delta x. Thank you. Yes. Factor out a delta x from the numerator to make it then -2 plus delta x all over delta x. Cancel out the delta x's. Okay. Now we have a bit of a new scenario here. In the previous problem, the delta x is completely canceled out. There was no place for us to direct substitute in the 0 for delta x, and so our final answer was just 3. Here, the delta x is canceled, but we still have a delta x left over. But what can we put in for that delta x? 0, right? We want to take that limit. So it's equal to then -2. And wouldn't you know, you guys were right. The slope at that point is negative slope. In fact, it's specifically the slope of -2. Okay, it's specifically the slope of -2. Okay? By a similar argument here, okay, if you want to do the at x equals 0, let's see here if I can I make that? Yeah, we'll do it. I just want to make sure because I think, yeah, we'll do it here. I just want to show the 0 one as well. I'll do this one a little bit faster though. Bless you. Okay, so again, the limit as delta x approaches 0, we'll say this is the slope at x equals 0. Okay. And I'm going to go ahead and plug in. So I'll say f of 0 plus delta x minus f of 0 all over delta x. Okay. which is then equal to the limit as delta x approaches 0. This is nice because 0 plus delta x we can actually simplify here, right? In the earlier one, -1 plus delta x doesn't really simplify, right? You had to leave it. But here at 0 plus delta x, it's just delta x. And so when I go to plug this in, I can make it just delta x quantity squared plus 1 minus, and then f of 0 we know is 1 from that point we've got, all over delta x. Okay. So again, I'll highlight these because I think that might be beneficial. F of 0 plus delta x becomes just this. F of 0 becomes just that. Okay. So this simplifies really nicely. The 1 and the minus 1 cancels. We have delta x squared over delta x, and that simplifies to just delta x, which is then just 0. And again, we confirm what we already intuitively thought was the case, that the slope at that point would be 0. Okay. Compare those instant slopes to the slope of the secant, okay, between from -1 to 2, 0, 1. Okay, the slope of the secant there, which if we just did the slope formula here, we could do, 2 minus 1 over -1 minus 0. We get 2 over, 1 over -1, which is then -1. Okay? So you'll see that, again, the secant slope, the slope between these 2 points that are relatively close to each other, it's a pretty good approximation, right? -1 is pretty close to both -2 and to 0. In fact, -1 is between those two slope values there, right? Here, -2 is the slope at the point to the left, and then we change to a slope of 0 at the right, and then the slope between those 2 points is -1. So, you can see the slopes are kind of close. The secant is a good approximation, but again, we have a way to do that precisely with a tangent. Okay, questions on anything so far? All right, moving on. So, the derivative of a function. The limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, differentiation. So this is pretty big, right? You're learning something that's akin to algebra, or addition or subtraction or multiplication or division. You're learning an operation here called differentiation, right? It's been a long time since you've learned some sort of new operation that you do with things, right? I feel like, at least anyway. So here we go, all right? So the definition of the derivative of a function. The derivative of f at x is given by f prime of x. So this is one way to denote the derivative, right? If you talk about f of x, the original function, its derivative is denoted as f apostrophe x, which is called f prime of x. Okay, f prime of x. And it's equal to the limit definition here. Okay? The process of finding the derivative of a function is called differentiation. Okay? A function is differentiable, that is, able to be differentiated at x if its derivative exists at x. And it's differentiable on an open interval a comma b if it's differentiable at every point in that interval. Okay? And of course, we'll talk about when things are not differentiable later, not today. Okay? So here are different notations that you're going to see to describe the derivative of y equals f of x. Okay? So we already talked about f prime. That's one way to denote the derivative of f. An alternative method here is this, okay, dy over dx. Okay? The notation dy over dx is read as the derivative of y with respect to x. Okay? Derivative of y with respect to x. This is kind of I think, a development from what the derivative really is. The derivative is a slope, right? How do you find the slope? Well, it is a change in y over a change in x, right? The rate of change in y over the rate of change in x, right? This little symbol here is the Greek letter delta, which is their d, and so we just change that to the English, dy over dx. Okay, so delta y over delta x, the slope formula is just dy over dx. The change in y with respect to x. Okay? And again, that idea then, with respect to x, we'll be taking the derivatives with respect to other variables. And again, it's not going to be mind-blowing. It'll just be a slight shift in our thinking. That's all. Also, we could call y prime. So instead of just saying, y is the original function, y prime. And then finally, this is another way. And again, it's kind of like just a manipulation of this. You can see that the y is just being replaced by f of x. And they don't put the f of x up in the numerators, but it's still read the derivative of f of x with respect to x. So here this was the derivative of y with respect to x. This is the derivative of f of x with respect to x. Okay, but just replacing the y with f of x there for that notation. All right, questions on any of that? All right, so let's keep going here, pressing on. So we're going to then find the derivative of f of x equals the square root of x. And then we're going to use that to find the slope of the graph at a couple points. Okay, so again, let's graph this. So there's 1, 1. There's 4, 2. Okay. But this time we're going to do things a little bit differently. Rather than using our derivative, definition of the derivative here, to find the limit at a specific point, we're going to find the derivative at a generic point, x. So we're not going to plug in 1 or 4 for the x at the start here. So let me show you what I mean by that. So here we'll do the derivative. Okay, so we'll say f, I'm going to go ahead and just denote this, f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay. And again, I am not going to plug in x values here. I'm going to leave the x there, and we'll just take the derivative using the generic x value. Okay, so f of x plus delta x, well, that's going to be the square root then of x plus delta x minus f of x, which is the square root of x, all over delta x, like so. Okay, so again, there's that substitution. Now, since I didn't put an x value in here, a value in for x, like in the past when I put values in for the x, we had a little bit more simplification that we could do. But now that I'm leaving this generic x in here, we really are going to have some difficulty with trying to simplify that, right? We can't quite cancel out the root x here and the root x here because it's root x plus delta x minus square root of x. And if I try and plug in 0 now for delta x, right, if I try and evaluate this limit, what am I going to end up with? We're gonna have actually 0 over 0, right? Because it'll be x plus 0, so it'll be the square root of x minus root x all over 0, so it's going to be 0 over 0. So what do we do now? How should we proceed? Give up? Multiply by the conjugate. Exactly right. We're going to use the strategies that we've already developed. That's why we utilize those strategies, because we're going to see them showing up here when we take these derivatives. Okay? So, right, we'll multiply by the conjugate here. Root x plus delta x plus root x over root x plus delta x plus root x. Okay, now if you'll permit me, I'm not going to show like all the, multiplying out of that. If, root x plus delta x times root x plus delta x is going to give us just x plus delta x now, right? The middle term is going to cancel because we'll have a negative root x times root x plus delta x and a positive root x times root x plus delta x. So the middle terms cancel, and we're left with the final term here. It's going to be a minus x. Okay, all over, and then we'll leave the delta x times the quantity root x plus delta x plus root x there. Okay, and now what can we simplify? The x's, they're going to cancel. You got it. So we're left with delta x in the numerator over delta x in the denominator, and again times the square root. Okay. I promise these will not be this tedious for the rest of calculus. We will learn shortcuts, but for right now, you have to endure the tedium. Okay? So I apologize, but that's the way it's got to be. Okay? Delta x is canceled. We're left with a 1 in the numerator. Whew. And now what should we do? We simplified things. I multiply the conjugate. Sorry? Plug 0 in. Direct substitute now. Delta x, 0 in for delta x. We get 1 over the square root of x plus the square root of x, which could be written equivalently as 1 over 2 square roots of x, right? Whew. That is f prime of x. Okay. Now we have a bit of a different kind of answer here. This solution, right, is not a single value. This is a function itself, right? It is itself a function. So we started with f of x equals root x. We took the derivative of it without doing it at a specific point. We're just kind of doing a generic point x. And as we found the derivative, we then found this other function that is the derivative of the original one there. Okay? And so this thing, you can think of it as the slope of f of x equal to the square root of x for any x value. Okay? Think of it like a generic formula, a formula for the slope of this specific function, square root of x. Okay? The slope of f of x equals the square root of x for any x value. So how can I use this? Well, so the tangent slope at, and I'll just put a colon here. And let's do the first point, right? We want to find the slope of the tangent line at 1, 1. Well, we'll just use our derivative. And we'll evaluate it at f prime of 1. Which is equal to 1 over 2 times the square root of 1, 1/2. So the slope at this point, 1, 1, has a slope of 1/2. The tangent slope there is 1/2. Okay? Let's try the other point, 4, 2. F prime of 4, right? Again, the y-coordinate has no bearing on the value of our derivative. It's the x-coordinate here. So we'll plug in 4 to our derivative, 1 over 2 times the square root of 4. Well, 1/4. So the slope here is 1/4. Does that make sense? Well, I mean, if you look here, right, this looks like it's more steep, right? It's like going to be a steeper tangent line, so 1/2 is steeper than 1/4, right? 1/4 is more flat, and so it does look like it's flattened out there some. So yeah, we can kind of convince ourselves of that. But of course, then it says, discuss the behavior at 0, 0. Okay. And we end up with 1 over 2 times the square root of 0, which gives us undefined. At this point, it's undefined. Okay. Which is like, okay, that's a weird behavior we haven't come across when it comes to the derivatives. But if we think about it here, remember that the derivative is like a limit. And here, this limit does not exist. Right? We can't find a limit as x approaches 0 here. Right? We have no left kind of end behavior there, left side behavior. So the limit would not exist there. And so the derivative is undefined. Okay? Derivative does not exist there because limit's undefined. Limit doesn't exist. All right? Questions on any of that? All right. I do want to get through this one more problem here. All right, and then we'll be done. I know I'm like cutting it close, but I think we can do it. So let's go. All right. So find the derivative dy dt for the function y equals 2 over t. Okay, so don't freak out just because we don't have any more x's now, right? We're just treating t like x. So you can just, in your mind, let t be the same thing as x here. Okay, so and I'll hold off on the graph because we won't worry about that right now. Let's just get the derivative done here. So instead of taking the limit as delta x approaches 0, we'll do the limit as delta t, right? Again, we're just replacing x's with t's. Approaches 0 of f of t plus delta t minus f of t all over delta t. Okay? And I do this, again, not to be like tricky or whatever, but this can throw people off when you just change the variables. It can mess people up. All right, so let's do our substitutions here. F of t plus delta t, so that's going to be 2 over, and then minus f of t, 2 over t. Okay, just like that. Again, change my colors up here, but you can still at least associate the right pieces together. Now what method do we need to use to evaluate this limit? Common denominator, right. So this one will multiply by t over t. This one will multiply by t plus delta t over t plus delta t. Again, you can see why we practice this stuff, right? This was stuff in the prerequisite, and so that showed up in limits, and now it's got to show up in the derivative too, okay? So this is why we did this. Okay. So we get 2t over t times t plus delta t minus 2t plus delta t. Oh, 2 delta t, sorry. The 2 distributes the t and the delta t there. So 2t plus 2 delta t. O over t times t plus delta t all over delta t. Okay. So what's going to cancel here now? The 2 t's, and we're going to be left with a negative 2 delta t. Remember, this minus in front of the fraction distributes to both terms there. And so those will cancel, and we're left with negative 2 delta t over t times t plus delta t. And if you'll permit me, instead of dividing by delta t, I'm going to change that to multiply by 1 over delta t. Okay? I don't want to skip too many steps, but that's what we would do. Okay? The delta t's cancel then because of that. And we have the limit as delta t approaches 0 of negative 2 over t times t plus delta t. And now finally, what can we do? Plug 0 in for that delta t. And so we're left with negative 2 over t squared. And that is dy over dt. Negative 2 over t squared. Okay? That is your change in y with respect to t. So what is the equation then of the tangent line at 1, 2? dy dt, this notation is a bit weird, right? When we had back here, we had f prime and we wanted to evaluate it at 1, that's easy. You just plug 1 in for the x, right? F prime at 1 is what you write there. But here, dy dt, there's no like parentheses to write in the value. So here's how we denote kind of evaluating dy dt at a specific value. You put this vertical bar here, and you put a little t equals 1, like a sub t equals 1. That is how you show evaluating dy dt, the derivative of y with respect to t, at t equals 1. And so that's going to equal negative 2 over 1 squared, which is just negative 2. So there's our tangent slope. And we can write the equation of the tangent line using point slope form. Y minus 2 equals negative 2 times x minus 1. And there's the equation of the line tangent to y equals 2 over t at 1, 2. Yep, I'm sorry. There you go. tangent to y equals 2 over t. The derivative is 2 over t squared, but we're tangent to the original function. So there it is. Whew. Okay. We made it just in time. All right. We will learn shortcuts for this, so don't fret if you're like, this is so much algebra. It is, but we'll learn more.